All right, as in any calculus class, now that we are done talking about how to graph a figure, okay, so maybe like analogous to like algebra 2, graphing more complex figures, and then talking about domain, range, limits. Now we are going to start on derivatives. So the difference is when we did chapter 12, we talked about vector functions, which were just curves in space. So we were allowed to, they were parameterized in terms of a single variable, time. But here we have surfaces in space, and our surfaces are created by inputting multiple variables. So we have multiple ways that we could think about the rate of change or the derivative. So what we're thinking about here is something called a partial derivative. It means that we're going to hold one of the variables, one of the inputs constant, okay? So basically assigning a constant to be equal to the other variable, okay? And then that kind of reduces the number of variables, the number of things that vary in our equation so that we can take a more traditional derivative. Now, what that looks like is us having a surface, which is this orange thing that I'm now highlighting in pink. Okay, this is some kind of surface. Maybe it's like part of a sphere, or an ellipsoid, whatever. Okay, so this is part of a surface. And we said, I'd like to see how this surface is changing specifically when x changes. So what we did is we said, okay, we want to isolate the effects of x. Okay, we just want to look at how x changes. So let y equal a constant. And that created a plane, an extrusion of the line y equals a number, okay, in the xy plane. In doing that, okay, if we let y equal to a constant, we kind of cut the plane at a certain location. That gives us, we cut the surface at a certain location. That gives us a two-dimensional curve. We've basically reduced a three-dimensional function down to a two-dimensional function by setting one of the variables equal to a constant. Okay, now this thing that I've highlighted in purple, okay, is a function of x and the constant y naught. Okay, so y naught is now held steady, and we can look at the rate of change along that specific curve. We have basically isolated how does z change as x changes. So that allows us to do things like, make tangent lines in certain directions, or find the slope, right? Find the slope. Now you can do the exact same thing in the other direction. Okay, so again, we've got some like curved surface going on here that I'm highlighting very poorly. Some curved surface. And now we'd like to see what happens when we set x to be equal to a constant. Okay, well that creates a line in the xy plane, which when we extrude it becomes a plane that cuts our surface down. And now our surface has become a two-dimensional function. I didn't do a good job illustrating that. But now that is a function of f of x naught and y. Y is still a variable, but we are holding x constant. And that allows us to find a change or rate of change of z in the y direction. Wow, I cannot draw a straight line today. There we go. Okay, so we can find more slopes. We can find, we're kind of just like, we're really looking at, and this is an example on the next page that I give, we're looking at the slope in the x direction or the slope in the y direction. We're looking at the rate of change of our variable z, specifically related to one of the two variables. That on the next page is kind of this application that I put here, right? When you're doing an experiment, any good experiment, you would like to isolate the effects of one variable, okay? What is changing one variable do to our overall experiment, right? That's the ideal, okay? We'd like to isolate, we'd like to hold everything else exactly the same and only change one thing. So I gave an example here that was like, okay, you want to see if you're looking at like pressure and gas and temperature. Okay, so we might be interested in the rate of change of pressure if the volume is held fixed, but the temperature is allowed to change. But what if we hold the temperature fixed and the volume is allowed to change? Okay, so just kind of looking at the effects differently. Okay, so here's another picture. But I want to point out one thing. We usually represent the slope in the x direction, or the partial derivative of the surface with respect to x. Notice that we're not using d anymore, okay? Because d, we use that like actual letter d to represent like real derivative, but we have to use kind of this curly d here in order to make sure that we tell the reader that this function f is dependent on more than just this variable that we're taking the derivative with respect to. Okay, so again, this one over here is holding x constant, and this one over here on the right is holding y constant. Okay, and so let's take a look. I'm going to do 2 quick examples to show you what that looks like. Oh, and don't forget, technically this is a limit definition of a derivative, but notice that the change is only happening in either the x component or in the y component, not in both. And that's what it means to hold either x constant or hold y constant. There are a lot of ways that we can represent this, but you will find that the most common are these ones. And yeah, maybe like you might also see like zx and zy. Okay, to kind of introduce, yeah, as a substitute for f. Okay, so what does this look like if I want to take a partial derivative? I'm just going to do the first one, okay, just to show you that we don't actually plug in a number for y, or we don't actually plug in a number when we're holding something constant. What we're doing is we're just pretending in our head that it is a constant. So when we take the derivative, okay, so let's take the derivative of this function here. When I take the derivative, and I'm trying to take the derivative of this first term, I see that I'm taking the derivative with respect to x, which means that y is a constant, which means that this is basically the equivalent of like taking the derivative of x cubed times, I'm making this up, but like 4. Okay, so this eliminates some of your need to do a product rule because y is a constant. It doesn't change. Okay, so my derivative, fx, will be 3x squared, okay, times y squared, because y was a constant. It doesn't have to change. I'm not doing the product rule. And if I did do the product rule, the derivative of y squared with respect to x is 0. Okay. All right, second one. So minus 4x, missed that. 4x, again, y, just kind of coming along like a regular constant, and then plus 3. Okay, so that's the derivative of this function with respect to x, the partial derivative of f with respect to x at any time. And I then specifically told you to plug in 2, -1. I do want to show you one other thing though. Okay, if I'm finding the derivative of the same function, now a partial derivative with respect to y, okay, now I'm holding x constant. So I leave x cubed. So my derivative here would be like x cubed 2y. And you can rearrange it. If you like your constants at the front, that's also fine. Okay, and then minus 2x squared, because the derivative of y is just 1. Now, what's the derivative of 3x with respect to y? Well, there's no y's in there. So basically 3x is being treated as a constant, and the derivative of a constant is 0. Okay? So anytime you are taking the derivative, a partial derivative, with respect to one of the variables, that means you're holding the other one, you're treating the other one as a constant. So we've got a bunch of examples here that I want to make sure that you go through in the field notes, but I also want to show you that we have second partial derivatives. And this is why we end up getting a little bit, because we have so many options, right? We get a little bit mixed up. But you can take the derivative 2 times, both with respect to x. You could take it both with respect to y, or you could do some mixed partials. Okay? So there are lots, you could keep you could keep going. Okay, with a function with 3 variables, you get 3 first partials and 9 second partials. We've got this kind of combinations formula. Now, something special here is if the two, like, what do I want to call them? I guess these ones are mixed partials. What these ones will be homogeneous partials. I don't know. Partial derivatives with respect to x and second partials with respect to y both times. If you add them together, they should be equal to 0. This is only for special equations. Okay, two-dimensional Laplacian equation. That will come up. If you want to look it up, go ahead and look up what a Laplacian equation is. But that just means we need to take the derivative of each function, and this is 2 separate problems here. Take the derivative of each function with respect to x 2 times and with respect to y 2 times. When you add them together, they should be equal to 0 if this is a Laplacian equation. And I said that it was. I said show that this is a Laplacian equation, so you know that you should be getting 0 at the end. Okay, so you would start off by taking the first derivative with respect to x. Don't forget to do the chain rule. Okay, so e to the ax times a. Then the second function is dependent on y, so I'm treating that as a constant. A second derivative with respect to x will be e to the ax. A squared sine of ay. Okay, let's do the second one. This one I also have to use the chain rule, but for the other function, e to the ax is dependent on x, so I'm holding it constant. Sine of ay times a, and then y equals, oh, wait a second. I forgot to take the derivative of sine. My friends, this is cosine. And then finally, negative e to the ax sine of a squared. So now I've got an opposite sign, so I know that it will be 0. Okay, so that's kind of just proving that something is a Laplacian equation. The last little theorem here at the end is Clairaut's theorem, and I wanted to clarify a couple of things. And this is about the mixed partials. So for a Laplacian equation, it's about the kind of single variable partials, second partials. For Clairaut's theorem, we're talking about the mixed partials, the fxy, fyx. Now, the most important thing for Clairaut's theorem is that if these 2 second partials are both continuous on the domain. Okay, and on the domain, I mean by a little disk D. Okay, so that could be, if you remember the pictures from the last lesson, okay, we talked about the domain of a 3-dimensional function could be an area in the xy plane, and maybe you're only looking at a small circle around a specific point. Okay, so if it's defined on the disk, contains this point, and the functions, these 2 mixed second partial derivatives are both continuous, then they should be equal. Okay, so this example here, first what it's asking you to do, and I'm not going to go through this one, look at the field notes if you would like, but by using this idea, okay, that they're going to be continuous, and why are they going to be continuous? Because the functions are made up of, polynomial terms, and all polynomials are continuous. Okay, so if I take the second derivative of both of them, I will be able to figure out what a is equal to. That's the first goal. Okay, by using the fact that the second derivatives, the mixed partials, are going to be continuous, I will be able to know what a is, and then I will be able to work backwards to figure out what the original function is. So your first thing would be to find fxy. Okay, so that would be taking the derivative of this one with respect to y and setting it equal to fyx, which is the derivative of this one with respect to x. Okay, once you've found that, you're finding out what does a equal. And once you found out what a equals, and you actually, I guess, didn't have to figure out what a equaled in order to do this, but then you would be able to take f of x. Say f of xy is equal to the integral of fx specifically with respect to x. Remember that this is the first partial where the derivative has been taken with respect to x. So you would need to integrate with respect to x to get back to the original. Now, one thing is there's no bounds here, so it's possible that the original function had a plus c. We don't have any information about an initial condition, so we're not totally sure about this, but we will just leave plus c at the end.